I'm going to take the opportunity in this video to just go through some astronomy kind of logical steps that tend to filter throughout the whole entirety of astronomy, mostly to do with their calculations. Now, I find that a really good starting point for a lot of astronomy is redshift. Now, redshift, as a result of the Doppler effect, when waves are moving towards or away from something, they're shifted. Now, in the case of the universe, everything is pretty much redshifted. It means it's shifted towards the red end of the spectrum, which means that from what we observe a wavelength, lambda. And that wavelength, lambda, has obviously become that because it's been shifted from another wavelength, what we'll call lambda 0. And that lambda 0 was what it was emitted as when that radiation was created by the star or the galaxy that we're looking at. And so actually we can create a new term, which is lambda minus lambda 0, which equals delta lambda, or the change in wavelength. And we can then create a fraction for this, which is the redshift fraction for a Doppler effect. Z is equal to delta lambda over lambda 0. Now that is pretty much the starting point for our thought process here, because the really important thing you need to know is that we pretty much know these values. This is observed. This is what we observe. When we look at a star, when we look at a galaxy, this is what we observe. However, this is what we know it should be, based on the spectra that we're getting. And the important thing here is that this gives off a fraction, and that fraction is equal to something very, very important. It's also equal to the velocity of the object that's moving to create this redshift, otherwise known as the recession velocity. And the recession velocity divided by speed of light is also equal to this z factor here. So we've got a really useful relationship here that allows us to work out the recession of a specific object in space. But there's more to be said from this, because we don't really, it's nice to know the recession velocity of something, but what we don't realize is that actually this has a use. And the use is that we can input that velocity into Hubble's law. So when we know the distance of a star or galaxy, and we know the recession velocity of it, we have the Hubble constant. And the Hubble constant leads us to a very interesting observation, because 1 divided by the Hubble constant is the age of the universe. Obviously, when the Hubble constant is converted from any other non-SI units. So, but that leaves a little bit of a hole, because I said, yeah, we know the velocity of this, but where are we getting these distances from? Well, we're getting these distances from, basically we're getting them from, let's move this up a little bit, the fact that in this distance is going to come from measuring distances to stars using what we know as to be standard candles. So standard candles are basically the stars that we know they have a known luminosity. And the importance of having a known luminosity is that we can use an equation that comes from, that I've derived actually in the previous videos, that you can go back and have a look at, that when we have a known luminosity, which is L, and that's divided by 4 pi times the distance squared, that will be equal to B, which is the apparent brightness, or i.e. the intensity of the light that we're looking at when on Earth. So the intensity of the light, or the apparent brightness, is equal to the luminosity, i.e. the standard candle, the known luminosity, divided by 4 pi d squared, where d is the distance to that galaxy in this case. Now the really important thing is what kind of standard candles can we use? So I'm just going to put a little note over here for what standard candles we can use. So standard candles come in the form of, really poignantly, Cepheid variable stars. Again, we've talked about these before in another video. Cepheid variables are stars that pulsate with regular period and so have a known luminosity. Supernovae. Now, the thing is about supernova is that certain types of supernova have very specific luminosities as well. So when we see these, we'll actually be able to know the luminosity of them and then use the luminosity, again, here, with the apparent brightness that we observe to work out the distance. It's a very simple equation, really, when you think about it. It's all about knowing that luminosity that's there. And so there are other things that you can use, and of course we'll just put a little caveat there. Obviously we have the parallax method, which you can also use to distance stars, but again it has a very big limitations, and we discussed those limitations in the video. So what else can we talk about? Now you'll notice that I've added a train going up off here about the kind of thought process that we can employ when looking at astronomy. Now, you can be asked any number of kind of parts along this. Now, one of the things that is often seen with age of the universe is that they might get you to work out Hubble's constant from a graph. And the idea that Hubble's constant graph is a graph of V against D, and the gradient of that graph is Hubble's constant. So it's just worthwhile bearing in mind that sometimes they might ask you to work out a gradient, but beware of the units. Make sure that you get them changed into meters per second and meters before you start meddling with this, because otherwise you'll make mistakes. So the other train is that we can actually take a little offshoot thought process down here. And that thought process will be along the lines of thinking about a different use for this ratio. And actually we need to break this ratio up back down to a bit of a simpler version. And actually what we can notice is that this Z factor is equal to, yes, delta lambda over lambda 0, but that's also equal to lambda over lambda 0 minus 1. Now, you can test that kind of mathematics any way you wish. You can throw numbers into that to prove that that's the case, but it does work. And so as a result, this fraction here is a really interesting fraction, because this fraction relates to the size of the universe. Yes, you heard me right, the size of the universe. Because what we introduce now is something called the cosmic scale factor. And the cosmic scale factor is just as you see here. I'm just going to drop this down a wee bit more so you can see what I've written. So we've got the cosmic scale factors here. Now, one thing that you should note is this is the radius, or supposedly, very loosely termed, the radius of the universe. Now, that might seem a really grandiose kind of value, but it is the case. Because think about it. From previous video, we talked about the change that we observe. This is what we are observing. And this is what it was emitted as. And if you think about this as a fraction, this is what we've observed now, and this is what was emitted. this is kind of an indication of how much the universe has expanded over the time it took to actually create that observed wavelength. And so as a result, at a time when the radiation was emitted, the universe was this size. And now it's this size. And so hence the fraction makes sense. And one thing you can obviously pay attention to is we can use this to indicate how much bigger the universe was when this happened. And what's really interesting is we can then relate the z factor to this fraction as well, which is often very useful because we often get to this z factor, this Doppler shift factor here, before we get anywhere else. And so as a result, we have a new equation for z, which equals r over r naught minus 1. And so, for all intents and purposes, z plus 1 equals r over r naught, which is an indication of how much bigger the universe has gotten. Okay, so this is a really, really useful kind of calculation to indicate the proportion by which the universe has gotten bigger. So whatever this value equals is how much bigger the universe has gotten since this radiation was emitted and it became this value here. And this is called the cosmic scale factor. A very interesting factor to say the least.